You ever stop and think about this? A day on Jupiter is less than 10 hours long. That's less than half a day on Earth. But here's the kicker. Jupiter is huge, over 1,300 times bigger than us. How is that possible? Well, it's a real cosmic puzzle, and the answer, it's going to show us some of the incredible forces that shape the biggest objects out there in the universe. And you don't even have to look far to see how weird this is. Just check out our own cosmic backyard. Earth and Mars, the rocky guys, their days are pretty similar, both around 24 hours. Makes sense. But then you look at the gas giants, Jupiter and Saturn. Whoa, we're talking about a day that's only 10 hours long. These giants are just spinning at an incredible speed. So this isn't just some fun bit of trivia you'd hear on a game show. Nope. This is actually a major open question for planetary scientists. See, if we can figure out what sets a planet spin, that tells us a ton about how it was born and how it grew up over billions of years. Okay, so what gives? How in the world did these enormous planets get to be spinning so much faster than the little rocky ones like us? Well, the first part of the answer, it's actually something you can probably picture pretty easily. It all has to do with something you've definitely seen before, probably during the Winter Olympics. Yeah, we're talking about the ice skater effect. Okay, the fancy physics term for this is conservation of angular momentum. But don't worry about the name. All it really means is this. If something is spinning and you pull all its weight in closer to the center, it has no choice but to spin faster. It's a fundamental rule of the universe. And this is exactly how a gas giant gets spinning so fast. So imagine this. First, you get a solid little core of rock and ice. Then, once that core gets big enough, its gravity becomes this massive vacuum cleaner, just sucking in enormous amounts of gas from the disk of stuff swirling around it. And as all that gas gets pulled inward, closer to the center, you guessed it, the whole thing starts spinning faster and faster and faster. It's the perfect analogy, right? The skater with their arms stretched way out is like that big, spread out cloud of gas. Then they pull their arms in tight, and whoosh, they're spinning like a top. That's the gas being pulled in by gravity, forming a dense, fast-spinning planet. So the logic seems simple. More mass equals a faster spin. But, and this is a big but, the story doesn't stop there. Because to see where this simple idea completely falls apart, we've got to look past planets like Jupiter. We need to look at something even bigger. Let's talk about brown dwarfs. These things are the heavyweights of the planetary world. Think of them as being stuck in the middle, way more massive than a planet like Jupiter, but just not quite massive enough to ignite and become a star. That's why they get this cool nickname, failed stars. So if we stick with our ice skater logic, this should be a no-brainer. A brown dwarf is way, way more massive than Jupiter. It must have pulled in way more gas to form. So it should be spinning even faster, right? I mean, that's the obvious conclusion. Except it's totally wrong. In fact, it's the complete opposite. The most massive of these objects spins slower, way slower than smaller gas giants. And when astronomers figured this out, it just threw a giant wrench into everything they thought they knew. Clearly, something else was at play here. And that something else turns out to be an incredibly powerful, totally invisible force that's slamming the brakes on these spinning behemoths. And look no further than a system called HR 8799 for the perfect example. It's a great case study. In this system, there's a gas giant planet, and orbiting with it, a brown dwarf. Now get this, the brown dwarf is more than 3 times as massive as the planet, but the little planet is spinning 6 times faster. That right there, that is the whole puzzle in a nutshell. So what is this mysterious break? Well, researchers are now pretty convinced it's all down to a ridiculously powerful magnetic field. Here's the key. The bigger and more massive an object gets, the stronger its magnetic field becomes. So back when these objects were young, they were surrounded by that big disk of gas and dust. Their powerful magnetic fields reached way out into that disk and basically grabbed onto it. This connection created this immense drag, acting like a giant brake and slowing the whole thing down over time. So what this all means is that a planet's final spin speed isn't just about one simple rule. It's the result of this epic, cosmic tug of war between 2 opposing forces. And the result of that battle? It gets locked in, frozen in time for billions of years. So let's break it down. You've got these 2 forces fighting it out. On one side, you've got the spin-up force. That's the ice skater effect, accretion, pulling in all that mass and trying to make the planet spin like crazy. But on the other side, you have the slowdown force, magnetic braking, which gets more and more powerful as the object gets bigger. The spin we measure today, that's just the final score from that ancient battle. And here is the beautiful part. The proof is in the data. When astronomers went out and measured the spin of a whole bunch of giant planets and brown dwarfs, they found something amazing. It didn't matter how massive they were all spinning at a similar, kind of slow fraction of their theoretical breakup speed, the speed at which they literally fly apart. This points to one thing: a universal mechanism. That magnetic brake is regulating everybody. And just how good is this brake? Well, on average, these giant worlds are only spinning at about 13% of the speed that would rip them to shreds. Think about that. It means this magnetic braking system is incredibly efficient. It gets rid of a huge amount of rotational energy, basically saving these planets from spinning themselves to death as they're being born. Which brings us to this really beautiful idea from the research. One of the scientists, Dino Chichun-Haas, put it perfectly. He said, spin is a fossil record of how a planet formed. Just think about that. By simply measuring how fast a distant world is turning, we're basically reading a fossil. We're uncovering the story of its chaotic birth, that epic struggle between the spin-up from gathering mass and the slowdown from its own magnetic field. It's a pretty mind-blowing thought, isn't it? The length of a day on some alien world isn't just a number, it's a window into its deep ancient past. And if something as simple as a planet's spin can tell us a story like this, it just makes you wonder, what other cosmic secrets are written in the stars, hiding in plain sight, just waiting for us to figure out how to read them?